Okay. Okay. So, good afternoon. Now I'll talk about the satellite toolbox. Now it's the beginning of the aerospace mini symposium. First of all, do you want to say
Yeah,
something?
sure. Hi, I'm Orestes. This is Romanos, and this is Alberto. Alberto works in he's employed by the European Space Agency, and we also work in an SME in the aerospace sector. Yeah, sure. This idea of bringing people together and seeing if we can hold a mini symposium was mainly because we know that there are people that are actively using Julia in aerospace, maybe in isolation, and we wanted this to serve as a kind nudge for people to get to know each other and maybe spark some interesting conversations. So besides the talks, you're more than encouraged to talk to people and see if there's any common ground, and maybe there's enough people that are interested in these kinds of things that a small community might see the light of existence. Ronan, I think you could briefly reintroduce yourself because the talk will be recorded, I guess.
Okay.
So, yep.
Okay. Perfect. So, good afternoon again. So the idea here is to show this ecosystem called Satellite Toolbox. I'll go very brief for the background and history of the package, the current state, and then we go to some examples. I'm not sure if I can show the three examples, but the two first, probably yes. Okay, so for those who don't know me, my name is Ronan Arraes. I'm control automation engineer. I have a PhD in system control. Since 2013, I'm with the Space System Divisions at the National Institute for Space Research in Brazil, where I am the mission architect of the Amazonia 1 satellite and also the technical lead of the attitude on orbit control subsystems. In the Julia ecosystem, I developed some packages like satellite box, reference frame rotations, pre-tables, and some others. Okay, so a little bit of history. I had a two-language problem, of course. I had two-language problem during my PhD in 2011, 2012. I have to simulate a swarms of UAV to perform distributed estimation. Each UAV has at least 15 states, and the initial version code in MATLAB. And when I run through the Monte Carlo simulations with a lot of realizations, it would take 6 months to get the first version of the results. It would be unfeasible for a PhD. So I need to port every single function to C using that Cmax interface to bring the time down to 2 weeks. And in 2013, I joined INPE, and I found about Julia that was supposed to solve this very problem I had in my PhD. So to learn Julia, I started to code a lot of satellite-related algorithms, and also to learn about the attitude control and orbit dynamics. And in 2014, I published the very first versions of those packages in GitHub called SatToolbox and Rotations, which is not the package we now have called Rotations. And later, I renamed it to Satellite Toolbox and Reference Frame Rotations, which was moved to that organization in GitHub called Julia Space. So just for historic purpose, this was the very first commit of SatToolbox. By that time, Julia was in 0.3 release candidate version. Those were the times where things was breaking every week, okay? And then in rotations was also by the same time. And now we have everything in this organization called Julia Space. So since then, Satellite Toolbox received a huge number of functionality, mostly because of this mission we launched in 2020, Amazonia 1. We are using daily to perform numerous of space mission analysis. This is the core of our validate OCS simulator, which we use it to find failure scenarios for the Amazonia 1, and I presented in previous JuliaCon, and also to develop our next generation AOCS system. Okay, so current state. The very first issue in the satellite toolbox was, can you consider breaking it in several components? Because it was a huge code, a lot of things. The loading time was very big, especially on this time. After just 5 years, I managed to do this, to close these issues when I split all the components into smaller packages. So you just need to load the ones you want. If you load satellite toolbox, it loads everything. And you also have the satellite analysis with some analysis functions. We also have 2 companion packages, which is reference frame rotations, and spacing is to fetch data related to space weather, things like that. All packages are heavily tested and sometimes well documented. So I make sure that the coverage is always up higher than 98%. And we have documentations sometimes and doc strings and so on, so you can check how to use each function. But okay, the idea here is to provide some examples to see how we are using Satellite Toolbox daily, what we can do. This is just very simple examples, but I think will be important. So let me find here. Okay, is the size good? Yes, okay. So in this very first example, we want to plot the ground track of the ISS. We, during mission analysis, use this a lot. We want to see where the satellite is passing. So let's say we want to plot the ground track of the ISS. The very first thing we need to do is to load this package called satellite analysis. It already exports all the symbols inside the satellite toolbox. To plot the ground track, the first thing we need to do is to obtain the satellite, the object orbit. In this case, the ISS orbit. We have something called TLE fetcher, which fetches TLEs. The only fetcher available right now is Silestrack. So here we are creating a TLE fetcher using the Silestrack interface. We asking it to fetch all the TLEs that has the name ISS Zarya, which is the ISS, by the way. And we're just getting the first TLE. Sometimes the fetcher can provide many TLEs for past instance, but in this case, it just provides one, the most recent one. So running this, I have connection. Yes, I have. So it's going to Silestrack, fetching the TLE and showing here. So this is the current orbit, the most recent orbit we have for the ISS encoded in a TLE. Well, okay, so now we have the orbit. We need to propagate this orbit to plot the ground track. Since we are using the TLE, we need a SGP4. In Satellite Toolbox, we have many propagators, J2, J4, two-body, but in this case, we need to use the SGP4. So we call it propagators init with asking for the SGP4 and pass the TLE we just obtained. So here is the propagator. And now we have this very nice function called ground track, which just computes the ground track and gives to you in a very big vector. So here I'm propagating the orbit for 2 days. In the first version, in the first line here, I'm asking for the ascending orbits, and in the second for the descending orbit. So let's run here. So these are just a vector of tuples with latitude and longitude, nothing fancy. Here also. And okay, so now we have the ground tracks, but it's important to see the ground tracks. So since Julia has this very nice feature called extensions, we now can load, if we load GeoMachi and Chiron or in some backend of Machi, we enable those kind of extensions without requiring the user to install Machi if they did not want. And if we then load GeoMachi and ChiroMachi and ask to plot the ground track, we will see the ground track. Oh, it's pre-compiled. I should have done this before, but okay. And it's supposed to show here the ascending ground tracks. Let's go. Okay. So here you have the world map. No, let's just reduce some here better. So you have the ground track and all the ascending ground tracks of ISS during 2 days. Of course, we can do the same thing for the descending round tracks. Inside satellite analysis, every function that plots something has this in-place version where you can pass a Mach axis and it will plot just on top of it. So using this kind of interface, we can plot the ascending ground tracks and then plot the descending ground tracks on top of it. So if I do this, we have this very nice view of how the ISS is going in the next 2 days. Okay. But that was just very easy, right? You just use this function called ground track and everything is available to you. Let's go to a more detailed step by step how to compute this ground track, because we'll go through some very important functionality in SatelliteToolbox. What ground track is doing is propagating the orbit for the instance we want. Those propagations are represented in a inertial frame. We need to convert it to a Earth fixed frame so that we can obtain the latitude, the longitude, and the altitude of altitude is not important here, but okay. So you obtain those points. How you do this in SatelliteToolbox? The first thing, you need to define a time vector. How you want to propagate. Here we are propagating for 2 days using 1 second of time step. Let's run here. No, sorry, I think I here. So. Okay, plot. And it just propagates the orbit for 2 days every second. In this case, it's everything is happening with multiple threads, so it's very fast. And then you get these 2 vectors here. The first with the position, the second with the velocity. We do not need the velocity, just use the position. What we need to do now is to convert this inertial frame to an Earth fixed frame. This is a very important part of SatelliteToolbox, this kind of frame transformations. When you're working with satellites, you have these many numbers of reference systems. For example, if I just type here this function that converts an Earth-centered inertial frame and Earth-centered Earth-fixed frame. Sorry. 2. You see, you have just these numbers of reference frames. So it's very important for us. I use it every day. It's probably the most important feature for my work is this kind of reference frame conversions. So what we're doing here is, let's take the Julian day of each propagation instance. So here I get in the epoch of the propagator and adding the number of seconds for this propagation instant. Then we create the direction cosine matrix that rotates the TEM reference frame into the PEF reference frame. It's just two frames. One is inertial, other is Earth fixed. We convert the vectors and return it. So if I run here, I have all those vectors represented in the Earth fixed frame. And now we have this function also in SatelliteToolbox that converts some Earth-centered, Earth-fixed frame to geodetic coordinates. It can use different kind of ellipsoids, but we are just using the WGS84 here. After that, we just need to extract the latitude and longitude and plot, converting, of course, to degrees. And if you do this, we get this very ugly plot here with those lines and so on. But let's try to make it look a little better. You have inside satellite analysis this function called plot world map, which plots the world map in a blank canvas. So we just have the world map here, and you can start to adding the analysis you want. So we take this axis with the world map and just plot the lines we just computed. It will be somewhat better, but still very ugly because you have those horizontal lines. This happens because the point here in the right is the same point in the left, But Mackie does not do that. So when I plot in here, then I plot there, it draws this horizontal line. I can use a scatter plot or something like this, but that's why I create that function called the ground track, because it adds not a numbers everywhere when this happens, so we don't have these vertical lines here. Okay, so this is what I want to show about the ground track in the ISS. This is go through some features here. So I have time, so let's move to the second one, which is very nice to check where and when we can observe the ISS in the sky. Okay, so let's see how we can compute what I call the observation possibilities of the ISS from the city of Eindhoven here. To check this, of course, the first thing I need to do is to propagate, the orbit as we just did, convert to a fixed frame, Earth fixed frame as we just did. But here is a minor difference. We have to represent those position vectors in a local frame here at Eindhoven. And we use what's called NAD, which is a reference frame that where I'm standing, the X points towards the north, the Y points towards the east, and the Z points towards the center of the Earth. And then we feature all the instances where the elevation is this angle here between the horizontal and the ISS, is above 30 degrees so that we can have a clear sea in the sky. And the local time is between 21 and 22, which is about the time where the sun is setting here in the Eindhoven. Of course, we can do this in the morning, but just let's say that we don't want to wake up too early. And here's how we compute the elevation. So first thing we need to do, the same thing we did for the ground track, initializing the fetcher, getting the TLE from the internet, and propagating and creating the propagator. Okay. So now we have the propagator. And here we are doing exactly the same thing. I'm not going to details again. Just taking the position vectors and transforming them to a Earth fixed representation. Now we have something different to do, because we have all those vectors in a system that is fixed to the center of the Earth, and we want to convert it to a system in which its origin is at our current position here. So SatelliteToolbox has a function to do this. If you call this function here ECEF to NAD, it of course converts the Earth fixed frame to the local frame NAD. But you have this keyword called translate. If this keyword is true, it will translate this vector from the center of the Earth to our current position, leading to what we want to compute the elevation. So we just need to run this function here, and then we have those bunch of vectors. And now we need to filter. We need to obtain those instances that the elevation is larger than 30 degrees, and the time is right. Because if you see the ISS at the noon, we won't see the ISS. It's just too clear. There is too much light here. So the first thing we need to do is to obtain all the instants in which we propagate the orbit. It's very easy. We just get the propagation epoch, add the propagation time steps, convert to Julian to a daytime object, and add 2 hours, because everything here happens in UTC. We are 2 hours ahead UTC here, I think. Yes, I think so. And then you have those 2 million elements here, because we propagate for 1 month. I didn't mention that, but the propagation happened for 1 month. We also need to compute the elevation using this equation here, this simple equation here, just to obtain this angle between the horizontal and the ISS. So we compute here. And now we need to filter the moments that we had an elevation larger than 30 degrees, and the time is right, between 21 and 22. I like to do this using a data frame. So we are loading data frame meta here and added those 2 information inside this data frame. I'm not a data frame specialist. Probably there is 100 ways to do this better than I'm doing here, but this is just how I do. So inside this data frame, we have all this instance, and I want to select all the moments that the elevation was larger than 30 degrees. The time, the local time, is between 21 and 22. Then I extract the observation day and observation hour so that we can combine them into a line which tells the moment that the observation will start and the maximum elevation we will see in the sky. Of course, we can add the azimuth so we can know where to look. But okay, let's just do this. And we run this, we see that we'll have an observation possibility of the ISS 4 days from now, with an elevation angle of 30 degrees, more or less. And also at June 20 here, we will have a very nice observation. The ISS will pass just above our heads here, with a maximum elevation of 84 degrees. And well, this is how we obtain the observation instance for the. You can compare those numbers for those information you find online. It's matched pretty much well. Well, unfortunately, I think we do not have time for the third example. I think it's better just to discuss with you if you have any questions. So this is all. Thank you very much. As I would have to have more time for the third question. So sorry, the third example. Sorry.
Yep. Okay. So first of all, congratulations. This is a very useful package that a lot of people are using. My main question would be about what you think is the status of the ecosystem going forward into the future. What are your plans for it? You know, if there's a lot of things you want to keep on adding, on whether you're just focused on maintaining what you already have. And maybe, you know, this is a good opportunity for you to address people who are using the package to also contact you for a reference, as you've said earlier.
Yes.
Yep.
So I consider the ecosystem stable. We are using it every day. We launched a satellite with the analysis it provided. Everything matches. It's used inside the satellite simulator, which was validated with data from orbit. So I consider that everything that is on those packages now, it's stable, production ready. Further things we want to do, there is a lot of things. My next endeavor will probably be a high accurate orbit propagator, numerical orbit propagator. It was very nice that Julia now supports those kind of extensions, because to use this, to implement this propagator, I wouldn't have to use the differential equation, which is a huge system. I don't want to have this huge loading time for small analysis. So now that we have these extensions, I can use it to perform this propagation. Besides that, we have a lot of to implement in the part of, so the toolbox, the ecosystem, let's call it that, is divided in two parts. There's the toolbox, which is just functions, and the analysis, which take those functions and wraps into user for analysis. In the realm of analysis, probably I will tackle some kind of coverage system, developing something that you can put a mission, a sensor on the satellite, and it tells what parts of Earth is covered during some time. So this is probably the next steps. The other thing you said?
Maybe you wanted to address people listening to the talk either in person or in YouTube, if they're users of the package, maybe.
Okay, so sure. Thank you very much. It would be very important to me if you can send me by mail or a message in Slack. So if you're using SatelliteToolbox and why you're using SatelliteToolbox, it would be very, very important to me to show at INPE. It will be a very nice feedback. The adoption of Julia in the early days was somewhat difficult. Things are very improved a lot. Now Julia is standard INPE for mission analysis and attitude control analysis, but having this kind of feedback just helps a lot. So if you can do this, I would appreciate.
Hi, and thank you for a great talk. A usual problem for these kinds of missions is reference frames and their conversions. So in the Satellite Toolbox package, position vectors are just vectors. They don't encode the reference frame that they're supposed to be in. So have you considered doing something like unitful and having some subtype of vector, of abstract vector, that also encodes the reference frame that the vector is supposed to be in?
This is very nice. I thought, of course, when I had the very first version of those conversions, we didn't have a uniform or something like that. So having a vector, if you can do this without losing speed, it would be very nice to add this kind of information to the vector. So we know. Sometimes it can be very difficult because, for example, if you are using a J2 opt propagator, the reference frame will be the ones that especially define in the min element, so it can be anyone. So maybe define it there. It's something I thought, but it would be very difficult to add now that everything is coded, but it will be a very nice addition to the system because it will reduce the errors. But just keep in mind that this is a project I really want to do it sometime. I'm also asking for funding, is to build a small satellite, a CubeSat, where we can embed Julia inside it. So instead of having the attitude control system in C++ and having this two-language problem where we code in Julia and then to transform it to C++, put Julia inside this CubeSat to validate the concept. It will be very important to do this. I'm trying to do this. It will use functions in SatelliteToolbox, so everything must have a good performances. So this will be implemented. We can implement it as long as it does not hurt the performance or add some kinds of instabilities or something. Okay, but it's a nice suggestion. Thank you.